Hello everyone, welcome back to another lecture video for Math 110, Introduction to Number Theory. And in today's video, we are going to talk about linear congruences. So recall that last time what we talked about were congruences, which was this notation, A is congruent to B mod n, or A is congruent to B mod n, to represent a divisibility property, which is that the difference of A and B is divisible by n. Or another way we can say it is that A equals B plus Kn for some K. And one of the things that is great about congruences is that they satisfy different arithmetic laws. So it's called modular arithmetic. So it respects addition and multiplication and subtraction and some types of powers. And then we also previously, before that lecture, we talked about linear diophantine equations. These were equations where everything in sight is an integer. And so we're trying to solve for integer solutions for these integer equations. So this time, we're going to, instead of using equalities and deal with equations, we're going to deal with congruences instead, and come up with some different ways of solving congruences that are linear in a similar sense to the linear diophantine equations. So the main idea underlying all this is that it's essentially what we've already done, just with some new notation. So because, well, A congruent to B mod n is the same as there existing some K satisfying this diophantine equation, what it turns out to be is that these linear congruences are actually diophantine equations where we introduce a bunch of additional variables and just don't care about their values. Okay, so here is the basic one that we're going to solve first. One variable, one equation, linear. So, and that's AX is congruent to B modulo n. And just as a side note, we could be considering, I guess, a more general sort of equation, which is ax plus b is congruent to c modulo n. But we can subtract b from both sides because of modular arithmetic to turn that into ax is congruent to something mod n. So anyway, we can just bring all the constant terms from one side to the other, and that is why we are considering just this case. Okay, so two motivating examples for these. Well, I mean, just examples. And we're going to see, they're going to motivate various features we're going to see along the way. Is 2x is congruent to 6 modulo 7, and 2x is congruent to 6 modulo 10. So let's just solve it in a brute force way, which is, so first of all, since we're solving this modulo 7, we only need to consider various residues of x modulo 7. So solutions, we may as well just consider them as ranging from 0 through 6. And to solve this in a brute force way, what we can do is look to see when is 2x, when's the remainder of 2x after division by 7 equal to 6, which is 6 is already equal to the remainder after division by 7. So in this table, I have 2x mod 7 all the way along, and it's a pretty easy table to make, so it's not so bad of a brute force thing for such a small number, where I just went along adding 2 each time, and then once I got past 7 I wrapped around back to 1 and then continued. And one thing that we can see from this is that 6 appears exactly once, so x is congruent mod 7 to 3. That's the only solution. Modulo 7. Now let's look at 2x is congruent to 6 mod 10. So again, we make a table 0 through 9 for all the possible residues of x. And so then 2x mod 10, we take the residue, and we have 0, 2, 4, 6, 8, 10. So 10, remember, is 0 mod 10. So then it wraps back around, and we have the same pattern again. And we can see that 6 appears twice. So modulo 10, the two solutions are 3 and 8. Okay, so one thing to understand, what we're aiming to understand, is why is it that the first equation has only one solution and the second equation has only, the first congruence, they're not equations, has only one solution and the second has two. The other thing is, can we find these solutions without doing anything brute force, like by making a full table? So that's our goal, our immediate goal. Okay, so let's recall that AX congruent to B mod n is equivalent to there existing a y in the integers such that AX plus ny equals B. This was a lemma from last lecture, essentially. So then, our strategy can be, first, solve this linear diophantine equation, which is something that we know completely how to do now, and then we just forget about y. So that's the basic strategy, and then we just kind of tie it up into a nice little package so that it's easier to apply than having to actually introduce this additional variable. So one thing that we saw was that these linear diophantine equations have solutions exactly when the GCD of the coefficients, in this case a and n, divides b. So when the GCD of a and n does not divide b, then there are no solutions. And we're going to focus on the case when it does divide. One remark, just because it's nice to see how these things respect modular arithmetic, is that like in the Euclidean algorithm, we can take one of the two numbers mod the other to get something with the same GCD. So if we replace a with something else that it's congruent to, for example a mod n, then, well, of course we get the same congruence according to modular arithmetic, but also it's the same GCD, so this condition doesn't actually change. So that's just a nice thing to consider. Like before, when we were doing diophantine equations, we're going to look at the homogeneous case first, and then look at what happens when b is not 0 to get the general solution. So for the homogeneous case, that is when AX is congruent to 0 mod n, and also we'll just assume that n is positive. In particular, we want it to be positive just to simplify things. And also let's assume that a is not congruent to 0 mod n. So in particular, like a is non-zero, just for now. Like we observed before, this is equivalent to the diophantine equation with two variables where we don't care about the second variable. And also one thing to note is, like before with the diophantine equations, the GCD of an and n divides 0, so it does have a solution. But also, obviously 0, 0 is a solution. Okay, so by that lecture where this was all introduced, we can just regurgitate what the lemma was, which gave the entire solution set to this equation, and that is the set of all pairs where the first one is for x and the second one is for y, where k ranges over the integers. And so, since we only care about x, what we can then do is we'll throw away y. And so the solution set to this homogeneous linear congruence is the set of all negative n over the GCD of a and n times k, where k ranges over the integers. Okay, so that is a solution set, but it would be nice to be able to have something that is smaller in a way. Like this is an infinite set because, this is a non-zero number in general, and when you multiply it by, and you take all the multiples, then you get infinitely many numbers. But if we take it modulo n, all those infinite numbers are going to wrap around the clock, so to speak. And so what we want is this more efficient set of solutions, which is something where every single solution to this equation is congruent to one of these numbers, And also each of these numbers is, it's congruent to exactly one of these numbers. And also each of these numbers is a solution to the equation. So to get this, all we have to do is observe the following. First of all, n was positive, right? And and the GCD of a and n is positive. And that's because both a and n are non-zero. So that means that this is positive. So one thing to notice is that if we take only negative integers, then we're going to get, and also 0, then we're going to get non-negative integers from the set. And also, if we start taking them, so this is k equals 0, k equals minus 1, k equals minus 2, once we get up to k equals the GCD of an, and then that would be times n over the GCD of an, this one is congruent to 0 modulo n. So these numbers that we get, these residues of solutions, wrap around. So we're just left with these numbers. So the GCD of a and n counts the number of solutions, and these are them. Let's look at the homogeneous versions of the equations, of the congruences that we looked at in the first example. So the first is 2x is congruent to 0 mod 7. And we see that the GCD of 2 and 7 is 1. So there's only one solution according to the previous slide. And that would be when k is 0. So that's 0. Now what about the 2x is congruent to 0 mod 10? So we take the GCD of a and n, which is 2 and 10, which is 2. So there are two solutions. And we can calculate, using the equation from the previous slide, that the first one, it's always 0. And then the second one is 1 times 10 over the GCD, which is 5. And then the next one would be 10, but that's congruent to 0, so it wraps around. So this is what would happen if we kept going to higher and higher k, but anyway. Modulo 10, those are the only two solutions. Okay, so we assume that a was positive, and I just wanted to mention what happens when a is 0. Actually, we assume that just a was non-zero. So what happens if a is 0? Well, we know that we have 7 solutions in this case, so mod 7. 0 through 6, they all work, and every number mod 7 is congruent to exactly one of these. And also, one thing to notice is that this actually does match the equation that predicts the number of solutions, because the GCD of 0 and 7 is 7. And also, the equation that we came up with for finding those 7 solutions does happen to work for this, because this coefficient, the modulus divided by the GCD, is 1. So it's just k is 1, k is minus 1, k is minus 2, all the way up. So those are the 7 solutions. And that's just kind of nice because it makes this lemma easier to state without needing to deal with special cases for a. So let's suppose that a and n are integers and n is positive. Then what happens is that this congruence, ax is congruent to 0 modulo n, has the GCD of a and n distinct solutions when taken modulo n. And just to reiterate what they were, the solutions are given by 0 times the modulus over the GCD, 1 times the modulus over the GCD, and all the way up until the GCD minus 1 times the modulus over the GCD. I guess as a side note, we can write this solution, or this list of solutions, as a set. So k times n over the GCD, such that 0 is less than or equal to k is less than the GCD. Okay, so that is how you solve the homogeneous ones. Now what about the general case, when b is positive? Or I mean, when b is anything at all. So one thing was, well, we need the GCD of a and n divide b to divide b. But like before, let's try to reduce this to the homogeneous case by considering what happens when we have two solutions and use linearity properties. So consider their difference and multiply it by a. Because what I'm doing is I'm taking x1, which satisfies this, and x2 that satisfies this, and I'm just subtracting the two congruences from each other. But here's a way to write it without having to say what it means to, I guess, subtract two congruences. So I take a times their difference, and it's congruent to, but it's also just equal to distributing it. And then because x1 and x2 are solutions, then that's congruent mod n to b minus b, which is equal to 0. So a times the difference is congruent to 0 mod n, so that means x1 minus x2 is a solution to the homogeneous equation. So then, using the previous slide, then we know that the solution set for these differences can be described as all of these k times the modulus over the GCD for all these possible k. And then by adding x2 to both sides, we can then see that x1 has to be obtained from x2 for one of these k's. So that means that if we have a solution at all, then we can get all the other solutions by adding some multiple of the modulus over the GCD. And that's then how we get everything. So the question is, how can we get a solution at all? And just like how we did it for diophantine equations, we use Bézou's identity. And also, if you're doing, well, if you want to actually compute it, not just do it theoretically, then you want to use something like the Euclidean algorithm. So we have this equation we want to find a solution to, this congruence, and we know that the GCD of a and n divides b, and we're assuming n is positive. So by Bézou's identity, we know that there exists some integers c and d such that the GCD equals ca times dn. And then we can multiply both sides of this by b divided by the GCD of the a and n. And we know that this is an integer because of this divisibility hypothesis. So when we multiply it, I'm keeping the a and the n out because I want us to observe something. But we've got this coefficient, that coefficient, and then also when we multiply the GCD by this, we just get b. And now we take this all modulo n. So what I mean by that is, well, since they're equal, then we can replace the left and the right side by what they're congruent to mod n and get a congruence. So b is just b, but this n here, modulo n is 0, so this term is just 0 modulo n. So what we see is that this, whatever this coefficient is, times a is congruent to b modulo n. And notice that means that we've solved this equation after commuting these two numbers, where cb over the GCD gives one of the solutions. Okay, so to get a solution, basically we need to find this number c, which there are lots of numbers that are possible, and any one will do, but we need to find this c, which satisfies this, and then calculate c times b over the GCD. And then that's one of the solutions. And so, in summary, for this theorem, for how to solve these linear one-variable congruences, let's say that we have a, b, and n, which are integers, where n is positive. So there are two cases. Either the GCD doesn't divide b, or it does. And if it doesn't, then this congruence has no solutions. And otherwise, if it does divide, then letting c and d be two integers that must exist by Bézou's identity, such that the GCD is this integer linear combination of a and n using them, then we can write the solution set as c times b over the GCD plus k times n over the GCD for all k from 0 up to but not including the GCD. And so that's, of course, a solution set of ax is congruent mod n to b. And then the sense in which this is a solution set, well, it's a solution set modulo n, which by that like before I mean every solution to this congruence is congruent to one of these solutions, to exactly one of them in this set modulo n. And also everything in this set is a solution. So I guess one small warning, unlike the homogeneous case, this is not giving us a list of least residues. Like, it's not giving us numbers that are in the range 0 through n, not including n. So what we could do is, if we just wanted them to really be residues, then we could take the things in the set and take the remainders after dividing by n. Just a small note. Just didn't want you to think that we're promising too much here, other than we do have exactly the right number of solutions modulo n. Okay, now that we have that theorem in hand, let's solve the examples from before in this more rigorous way, where we don't make a table, you know. So we have 2x is congruent to 7, or congruent to 6 mod 7, and well, one thing is 3 is just an obvious solution for both of them. So we have a particular solution immediately, which is nice. But I just wanted to mention how we compute it with this more general method. So, the GCD of 2 and 7 is 1, just by looking at prime factorization, say. They're both primes. And then we can observe, I guess. Well, I just thought, well, 7, it's 3 times 2 plus 1. So I just wrote this down. I didn't want to do the Euclidean algorithm right now. We'll do it again later as a refresher. So, okay, so then the coefficient of 2, that is c. And so we take c times b over the GCD, and then that is the particular solution. And we calculate that's minus 18. And then just, I guess, one way to calculate this is I added enough 7s until it was just positive enough. So 3 7s, and that's 0 mod 7, so I'm allowed to do that. And 21 minus 18 is 3. So x is congruent to 3 mod 7, which matches the table that we computed. And this is the only solution because the GCD is 1. Now what about 2x is congruent to 6 mod 10? So the GCD of these numbers, again by prime factorizations, is 2. And in this case, whenever one number divides the other, then the Bezier coefficients are really easy. You take 1 of one and 0 of the other. So 2 is 1 times 2 plus 0 times 10. So that is that gives us our c, which is 1. So our particular solution is c times b over the GCD, 1 times 6 over 2, which is 3. And then we add the modulus over the GCD to get the next solutions, and that's 5, so 3 plus 5 is 8, and the GCD is 2, so there's only 2 solutions, so we stop after adding it once. And again, that matches the table, so that's good. Theory meets, I guess, practice. Well, practice in theory, I guess. So it's good to look at this other point of view too, and this is explored more in the textbook. And that is, there's a way to reduce an equation by using the fact that the GCD divides everything. So if ax is congruent to b mod n, and I'm using the parenthesis notation to give myself some more space to mess around with the modulus, then, well, the definition is that there exists a k, well, definition, then messing around with the equation a little bit, there exists an integer k such that ax plus nk is b. A, n, and b are all divisible by the GCD, by hypothesis. So we can divide everything by the GCD to get another equation involving this new diophantine equation. But then that is stating exactly that a divided by the GCDx is congruent to b over the GCD mod n over the GCD. So anyway, solving the first equation is in some sense equivalent to solving the second equation. And also, the second equation, because we've divided out by the GCD of the coefficient and the modulus is 1. So this equation, mod this new modulus, has just one solution. Let's call it x naught, or x0. So then all we have to do is, so that's the particular, then the way that all the other solutions come about from this point of view is that, well, that's the solution modulo this modulus, but we could also just, like, that's an integer, we can just take it modulo n too, and that's going to be a solution. But because all solutions according to the second congruence are all different by a multiple of n over the GCD, we can just add multiples of the GCD to it to get all the solutions of the first equation. So that's what happens here. So all solutions are congruent mod n to this particular solution that exists plus a multiple of n over the GCD. And we only need to take k in a particular range to get the k different solutions. Okay, so that's that point of view. And it's a useful one for what's to come, for solving systems of these. Now that we've seen how to solve individual linear recurrences with one variable, let's see how to solve systems of congruences with one variable, which is a very classic problem. So we have all these congruences, each with their own coefficients, each with their own constant terms, each with their own moduli. And so we want to solve these for x. So one thing that needs elaboration is, what does it actually mean to solve one of these? Because well, one thing is, if there's a solution at all, it does turn out to be that there are infinitely many solutions, and it's not so efficient writing down an infinite list of solutions. So here's what I mean by solving. So it means that we want to find some other modulus capital N, which is positive, such that for every I, Ni divides N for each I from 1 through M. So, and then we also want to find a collection of residues, modulo N. So numbers 0 through, so numbers 0 through capital N, not including N, such that whenever you have an integer x, then x satisfies the equations if and only if when we take that number modulo n, then it equals one of the numbers in the list of residues. So what this is saying is that, first of all, well, it is a complete list in the sense that x modulo n will lie among one of these. And secondly, each of these is a solution. So if we take these numbers and then plug them into each of these equations, then they solve them. And this is why we have this divisibility property here, that Ni divides capital N. And that is so that it makes sense to take one of these numbers mod n and then further reduce it to this smaller modulus. Okay, so let's simplify our problem. So we already did a bunch of work for dealing with these linear recurrences and how to solve them. So one thing is for sure, for this to be solvable at all, what we need is that the GCD of each coefficient by its modulus divides its constant. So if that's not true for any of them, then the whole thing is just not solvable. Another thing that we can do is, by that observation for that alternative point of view for how to solve these things, when the GCD is not 1, what we can do is take this congruence and then divide each of the three things by the GCD. So I'm labeling DI to be the GCD of AI and NI. Because this does not change the solution set. Because solutions to this second equation, or second congruence, are solutions to this first congruence and vice versa. So after making this reduction, we can assume that the GCDs are all 1. Okay, so since each of them has one solution, then we can just solve each of them individually. And so AIX congruent to BI mod NI, we replace it with XI is congruent to BI prime for whatever the solution might be, this BI prime. Okay, so now that we've reduced it like this is actually the systems that we'll consider now, where we have some number that modulo various moduli, we get various numbers. And let's see how this works with an example. So let's say that we have n squared ceramic tiles, and like bathroom tiles, and when they're arranged in a rectangle with 5 on one side, which is this yellow rectangle here, so 5 tiles on this side, and some number of tiles that we don't know on the other side of the rectangle, then we have 2 tiles left over. And when we make a rectangle 7 on one side, some other unknown number on the other, then we have 3 tiles left over. So what is the set of possible numbers of tiles that we started with? Okay, so changing this into a system of congruences, we're saying that x after dividing by 5 has remainder 2. So that we can equivalently say that x is congruent to 2 mod 5. And also x is congruent to 3 mod 7. So the key idea that's going to underlie the main theorem for all of this is this. So I've made this rectangle, which is 5 by 7. And in it, what I'm doing is I'm taking each integer one at a time, and then calculating its remainder, mod 5 and mod 7, and then putting it in that tile. So I'm taking its, so I guess, given x, then we put x in coordinate, I'll use square brackets for the coordinate, in x mod 5, x mod 7. So that's what I'm doing here. So 0 mod 5 is 0 and mod 7 is 0. And then each time I add 1, I'm increasing the remainder for each of them. So 0, 1, 2, 3. So 3, it's divided by 5, remainder 3, divided by 7, remainder 3, 4. But then when I get to 5, that has 0 remainder 5. So it wraps around. So like really, this is like this donut. So we're putting the numbers in on this donut. So going around like this. Going down, it wraps around, crosses over, and then continues, and so on. But anyway, so that's what happens when you have 2 clocks. It's kind of a fun and somewhat complicated shape. But anyway, so we get to 4, we add 1 to it, now the remainder mod 5 is 0, but the remainder mod 7 is 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. And then, so this has 34, I guess, has 4, it's 4 mod 5 and 6 mod 7. And when we add 1 to that, we get back to 0, 0. So 5 and 7 have the special property that when we fill out the table like this to put every number in its coordinate based on its remainders, then it fills out the entire table with 35 numbers. Now, this gives us a way to solve the original problem, and in fact a way to solve all problems for all possible remainders for 5 and 7. In this case, it's 2 mod 5, so we want something in the 2 row, and we want something in the 3 column, and we can see that 17 is there. And indeed, 17 mod 5 is 2, and 17 mod 7 is 3, and also no other number, 0 through 34, has these 2 remainders. So mod 35, it's 17. If and only if, actually, by this construction. And since we know this, we can actually now write out the complete set. So it's the set of all natural numbers of the form 17 plus 35k, where k is a natural number. So we might have 17 tiles, we might have 35 plus 17 tiles, and so on. That's as far as we can figure out without some more information. Okay, so these are the this is the sort of transformation we're looking at, taking 2 congruences and combining it into a single one. Okay, so the main tool for this that we have is the Chinese Remainder Theorem. It's also known as Sun-tzu's theorem, named after a Chinese mathematician who investigated diophantine equations in the 3rd century. Chinese Remainder Theorem is, for some reason, the most prevalent way it's ever said, and in fact, I'm not sure how many people would recognize it as Sun-tzu's theorem. It's sort of like calling Bézout's identity the European GCD theorem. Anyway, so I'm going to say Chinese Remainder Theorem just due to what everyone else is calling it. Okay, so the idea, as we saw before, is that if we have 2 congruences with a special property, then we can combine them into a single congruence. And what this theorem, the Chinese Remainder Theorem, gives us is that if the 2 moduli are coprime, then we can do it definitely. And if they're not coprime, we'll have to do our own work. It's just sort of inconclusive. So let's say that we have b1 and b2 and n1 and n2 natural numbers, where n1 and n2 are the moduli and they're coprime. Then the theorem says that there exists some natural number b such that for all x, actually, it doesn't actually matter that this is a natural number. All this theorem does is gives us some integer. There exists an integer b such that for all x, then x is a solution to these 2 congruences if and only if x is a solution to the single congruence. So x is congruent to b mod the product of the moduli is equivalent to x being equivalent to b1 or b2 modulo n1 or n2, respectively. Also, so this theorem, it only says that there exists a b, so you need to know the theorem and how to prove it to be able to actually calculate the b. So let's see how we prove this. Okay, so this is just a restatement of the theorem. And so the way that the proof goes is we first use the fact that the GCD is 1 to use Bézout's identity to get some integers c and d, where c times n1 plus d times n2 is 1. So there are 2 things that we can observe from this. And that's from taking this equation that we just got, modulo n1, and taking it modulo n2. So one way to say it is that we'll look at d times n2, then that is congruent mod n1 to c times n1 plus d times n2, because this term with this n1 is congruent to 0, mod n1. And then this we said was 1, so d times n2 is 1. Similarly, or congruent, it's not is, it's congruent to 1 modulo n1. Similarly, c times n1 is congruent to 1 modulo n2. So those are some key properties about these numbers that we got. So this is the b that we will choose, and this is the main part and the main, I guess, creativity here, which is we just take the first term and multiply it by the second constant, and we take the first term and multiply it by the first constant and add it together, and that just happens to work. That's a good choice for b. Right, so how do we know that this works? Well, I crammed it in down here, but let's observe a couple more things. One is that this is a solution at all, which is really important. So if we take b and take it mod n1, then n1, of course, is 0 mod n1. So by modular arithmetic, that's 0. And then dn2 mod n1, we just saw was 1. So b is congruent to b1 modulo n1. That means that substituting b in for x, the first equation is solved. And similarly, b is congruent mod n2 to, well, this equation reduced to mod n2, and that gives us b2 using the second thing that we found before. So substituting b in for x for the second congruence is a solution. And of course b is congruent to b, so there's nothing really to be checked there. But so this means that at least we should potentially believe that this should be the solution. Now we need to actually prove this. So we have this b. Now we want to show that actually whenever we have a solution, then this equivalence holds. So first, let's prove the forward direction. Let's suppose that we have some x that's an integer, which solves the first two congruences. Then one thing to notice, and this is the reverse of the reduction thing from before, where we divided by the GCD, we can multiply everything in the first congruence by n2. So n2x is congruent to n1, n2, n2b1, which I wrote here. And similarly, we can take the second congruence and multiply everything by n1. With that done, then let's look at b. So b, it's congruent, well, it's equal to its definition. And then n2b1, the second thing that appears here, is the same as n2x, and n1b1 or n1b2 is congruent to n1x, so we can replace n1b2 with n1x. Then we can factor the x out, and then the coefficient is equal to 1. So b is congruent to x modulo n1, n2. So the conclusion does hold. Great. Okay, now let's prove the converse. So we suppose that x is congruent to b modulo n1, n2. Then what we can check is that, well, x is congruent modulo n1 to b because, well, it's congruent modulo this number that is divisible by n1, so we can reduce it further. And then, well, b is congruent, as we saw, to b1 modulo n1. So x is congruent to b1 modulo n1. And similarly, x is congruent to b2 modulo n2. So indeed, what we needed to show has been showed there. So both implications hold. So it's a logical equivalence. So we've shown the conclusion with this b. Okay, so this is a theorem that you definitely should learn and be able to prove yourself. It's a useful sort of theorem, and also otherwise it's hard to remember how to actually calculate this b, I find. Let's look at an example now, and this is the tile problem. So x is congruent to 2 mod 5, and x is congruent to 3 mod 7. So 5 and 7 are prime numbers, so they're different, so the GCD is 1, so we can apply the Chinese Remainder Theorem. And we need some Bézier coefficients to be able to calculate our b. So I used the Euclidean algorithm. So I took the larger number, mod the smaller number. So 7 is 5 times 1 plus 2, so 2 is the remainder. So GCD of 5 and 2 is 2 and 5 mod 2. And 5 is 2 times 2 plus 1, so the remainder is 1. And the GCD of 2 and 1 is 1. Now we go in reverse, so 2 and 1, the GCD, we can write it as 0 times 2 plus 1 times 1. And then 1 is a remainder, and it's 5 minus 2 times 2. So we plug that in. Then rearrange to keep the 5s and 2s. Well, this 2 doesn't matter, or this minus 2. It's the second 2 that's like the real 2 for the GCD. Then 2 is 7 minus 1 times 5, which we can substitute in for that 2. Then rearrange to get that 1 is 3 times 5 minus 2 times 7. So the GCD of 5 and 7, which is 1, is equal to 3 times 5 plus negative 2 times 7. 3 and minus 2 are our Bezout coefficients. So 3 is C, minus 2 is D, using the letters from the proof. And then 5 and 7 are N1 and N2. So then the proof says that we can say that modulo 5 times 7, X must be C times N1 times B plus D times N2 times B1. So 3 times 5 times 3 plus negative 2 times 7 times 2. So that's 45 minus 28, which is 17. Probably making the table in this case was easier than going through this process, but not all numbers are just 5 and 7. Yeah, so it matches what we got from before, which is great. Now, the Chinese Remainder Theorem gave us a way to solve this for when we had two congruences. How can we join them into a single one? And when we have more than two, the idea is that, well, if everything in sight, or if all the moduli are coprime to each other, then we can repeatedly apply the Chinese Remainder Theorem, coalescing pairs of these congruences until we're left with a single congruence. And then we've solved the system. An important utility lemma for this is that if we have that A is coprime to C and B is coprime to C, then the product of A and B is coprime to C. So if you aren't sure why this is true, this is a great little exercise for you. Okay, so let's look at this system of three congruences. So X is congruent to 1 mod 3, and then mod 5 and mod 7, it's 2 and 3, like before. And then 3, 5, and 7 are all coprime. And I just made this sort of diagram up to represent which things are coprime to each other, which is all of them. So by the Chinese Remainder Theorem, being able to solve these latter two congruences is equivalent to solving the single congruence that X is congruent to 17 mod 35. And by this utility lemma, we don't even need to calculate anything. We just know that 35 is coprime to 3. And then that means the Chinese Remainder Theorem applies. And so modulo 3 times 35, we get X is congruent to something. I didn't calculate what it was, but rest assured it is congruent to something by that theorem. If only we went through the effort to calculate the B. Okay, so yeah, that's what the Chinese Remainder Theorem lets us do. It lets us solve these systems so long as all the moduli are all coprime to each other. Here's another example. So X is congruent to 7 mod 15, and X is congruent to 10 mod 21. And we run into a problem, and that is that the GCD of 15 and 21 is 3, so they're not actually coprime, so we can't actually apply the Chinese Remainder Theorem, at least immediately. But that doesn't mean that there are no solutions. It just means that, I guess it's inconclusive, using, I guess, some like calculus 2 words. And in fact, this is solvable. Like, we can just plug 52 in and check right now that it indeed solves the system of congruences. So here's a technique that you can use sometimes for still applying the Chinese Remainder Theorem. And that is, we look at the prime factorizations and then take the equations that we have and reduce them mod all the prime powers that we saw. In this case, they're just primes, so no prime powers. So 15 is 3 times 5. So by the Chinese Remainder Theorem in reverse, we can split it into two equations without changing the solution set. And 21 is 3 times 7. So we can, again, apply the Chinese remainder theorem in reverse to get two congruences that don't change the solution set. And we can see that according to 1, mod 3 it's 1, and mod 3 it's 1. So they do not conflict with each other, which is good. Because, for example, if this had been instead 2, then we would know that this thing had no solutions. But they possibly have a solution. So we can then take each of these, replace them by their lists of congruences, and then, I guess, well, mod 3, we have this equation twice, so we only need it once. So by the Chinese remainder theorem, this original system is equivalent to the one that we just saw before, with 3, 5, and 7. And again, then by the Chinese remainder theorem 2 more times, along with that utility lemma, we get a unique solution to this, modulo 3 times 5 times 7. So now let's summarize what we've seen and finish things off. So we were solving these linear congruences in one variable, and we did it by observing that there's secretly linear diophantine equations in 2 variables, and then forgetting about one of the variables at the end. And then we also looked at how to solve these systems of congruences. Using the fact that we know how to solve these sorts of equations, we only had to worry about, that's all supposed to be the same variable. We only had to worry about when one variable is congruent to various things modulo various other things. And we did this using the Chinese remainder theorem, supposing that modulo various, or that all the moduli are pairwise coprime. And when they're not pairwise coprime, we can apply the Chinese remainder theorem in reverse to split everything up. And then to finish up a solution, you recombine everything, make sure none of the equations are conflicting with each other. And if they aren't, then we can then apply the Chinese remainder theorem and then get a solution. So, yep, so that's that. I hope you enjoyed learning about this theorem, and also I hope you study the way this thing is proved. And I'll see you next time.